In the previous modules, we introduced the TEM Design Spiral and followed the journey from a need to a successful product. Throughout that journey, three words appeared again and again: explore, create, evaluate. But what do these words actually mean in engineering practice? This is where things become interesting. An engineer explores, creates, and evaluates during the thinking phase. The engineer does the same during engineering, and again during manufacturing. But the actual activities are very different. During thinking, we may explore user needs and alternative concepts. During engineering, we may explore mechanisms, components, materials, or technical architectures. During manufacturing, we may explore production processes, suppliers, tooling, and assembly methods. The same difference applies to what we create and what we evaluate. So in this module, we will look inside the TEM design spiral and examine what engineers actually do at each level. The words remain the same, but as we move up the spiral, the engineering work and the evidence we need changes. Explore, create, and evaluate occur at every level of the TEM design spiral. But there is an important point that we must understand. The words remain the same, but the engineering work changes as we move up the spiral. During thinking, we explore user needs, the problem, existing solutions, constraints, and possible concepts. We create requirements and alternative concepts, and evaluate whether we are solving the right problem in the right way. During engineering, our questions become more technical. We explore architectures, mechanisms, components, materials, and control methods. We create calculations, CAD models, simulations, and prototypes. We then evaluate their performance against engineering specifications. During manufacturing, the focus changes again. We explore production processes, suppliers, tooling, assembly methods, tolerances, quality, and cost. We create the production system and evaluate whether it can repeatedly produce the required product. Notice what is happening. As we move upward, uncertainty decreases and the evidence becomes stronger. Thinking builds concept confidence. Engineering builds performance confidence. Manufacturing builds production confidence. So the TEM spiral is not simply moving a design forward. It is progressively building the evidence and confidence needed to turn an uncertain idea into a reliable product. We now begin with explore at the thinking level. At this stage, exploration does not mean immediately searching for a better motor, a better sensor, or a better mechanism. We are not yet engineering the solution. Our first responsibility is to understand the problem deeply. Who are the users and other stakeholders? What do they actually need? In what environment will the product operate? What difficulties exist today? We observe users, talk to them, study the operating environment, gather data, and examine existing solutions. We also identify requirements, constraints, risks, and assumptions. And importantly, we ask why. Why does this problem occur? Why is the current solution inadequate? Are we seeing the real problem or only one of its symptoms? Only after developing this understanding should we begin exploring possible solution directions and technologies. At this stage, we should explore widely rather than quickly narrowing down to our first idea. The output is therefore not a finished design. It is a much clearer understanding of the problem, the needs, the constraints, the unknowns, and the possible directions we could investigate. This is the first discipline of good engineering. Explore the problem before you start designing the answer. Once we understand the problem, the next part of thinking is to explore possible solutions. A common mistake is to generate one reasonable idea and immediately begin developing it. Good engineers resist this temptation. Consider our washing machine. There are many possible ways to clean clothes. An agitator, a rotating drum, an impeller, ultrasonic assistance, or perhaps a completely different mechanism. At this point, we should deliberately generate alternatives. This is called divergent thinking. We can study existing products, patents, research, other industries, and even nature. We can brainstorm, use morphological charts, make simple sketches, and involve people with different backgrounds. The objective is not to prove that one idea is correct. It is to make the solution space larger. Only after exploring widely do we begin to converge, comparing alternatives and identifying the concepts that deserve deeper investigation. This distinction between divergence and convergence is extremely important. If we converge too early, we may spend months engineering a reasonable solution while never discovering a much better one. So at the thinking level, explore broadly first, compare carefully later, and only then commit engineering resources to the most promising concepts. After exploring the problem and identifying many possible directions, we move to create at the thinking level. But notice what create means here. We are not yet creating the final product, and we are not doing detailed engineering design. We are creating alternative concepts that allow us to think, communicate, and compare possible solutions. A concept might be represented by a simple sketch, a functional diagram, a rough model, a few calculations, or a very simple experiment. For our washing machine, we might create concepts based on an agitator, a rotating drum, an impeller, ultrasonic assistance, or an entirely different washing principle. At this stage, speed and variety are more valuable than detail. We should create several concepts using different physical principles and technologies rather than developing one idea in great detail. Tools such as brainstorming, mind maps, morphological charts, sketches, and simple mock-ups help us do this systematically. And most of these concepts will never become products. That is perfectly acceptable. Their purpose is to help us discover and understand the possibilities before expensive engineering work begins. So at the thinking level, create means create concepts, not commitments. We are making our ideas visible enough that in the next step, we can evaluate and compare them. We have now explored widely and created several alternative concepts. The next activity at the thinking level is evaluate. But at this stage, we are not yet asking whether the detailed engineering design works. That comes later. Our question is, which concepts are worth investing our engineering effort in? To answer this systematically, we first establish evaluation criteria based on the real needs and constraints we identified earlier. For our washing machine, these might include cleaning performance, water and energy consumption, expected cost, technical feasibility, technology risk, and scalability. We then compare all concepts using the same criteria. Simple tools such as a Pew matrix or a weighted decision matrix can make this comparison more objective. Risk assessment and preliminary cost-benefit analysis can also help. But we must be careful. A numerical score does not automatically make a decision correct. The criteria, their importance, and the evidence behind each score must themselves be sound. The purpose of evaluation is therefore not to manufacture a number that justifies our favorite idea. It is to expose strengths, weaknesses, assumptions, and risks so that we can make a better decision. The outcome may be one selected concept, or perhaps 2 or 3 strong concepts requiring further investigation. At that point, we have achieved something important. We have built enough concept confidence to justify moving upward into the engineering phase. We now move from thinking into the engineering phase. And notice how the meaning of explore changes. During thinking, exploration was deliberately broad. We explored the problem, user needs, and many possible concepts. Now we have selected a promising concept. Engineering exploration therefore becomes deeper and much more technical. We decompose the concept into systems and functions and ask, how will this solution actually work? For our washing machine, we now investigate the drum and drive mechanism, motor and transmission, bearings and seals, sensors, materials, structural arrangement, electronics, control system, and software architecture. We also investigate safety requirements, applicable standards, reliability, maintainability, manufacturing implications, and cost. At this stage, engineers use technical literature, data sheets, calculations, CAD layouts, simulations, experiments, component tests, and trade-off studies. For example, selecting a motor is not simply finding one that rotates the drum. We must investigate the required torque and speed, starting load, efficiency, thermal behavior, lifetime, control requirements, physical size, cost, and availability.
So engineering explore is different from thinking explore. Thinking asks broadly, what could the solution be? Engineering asks deeply, how can this selected solution actually be made to work? The purpose is to replace technical assumptions and unknowns with engineering knowledge before we commit to the detailed design.
We have explored the technical solution space. Now we move to create at the engineering level. Here, create has a very different meaning from the thinking phase. We are no longer creating alternative concepts. We are creating engineering evidence that allows us to understand, predict, and eventually prove how the selected solution will behave. And a prototype is only one form of engineering evidence. We might begin with equations and analytical models to understand fundamental relationships. We can use calculations to determine motor torque, power, loads, dimensions, or thermal requirements. CAD models help us examine geometry, interfaces, clearances, and assembly. Simulation allows us to investigate stresses, vibration, fluid flow, thermal behavior, electronics, software, and control systems before building hardware. When models are no longer sufficient, we can create experiments and test rigs to measure real behavior. And finally, when we need to study the integrated system, we may build a prototype. This leads to an important engineering principle. Do not automatically build the most realistic prototype you can. Create the simplest engineering representation that can reliably answer the question you need answered. As uncertainty decreases, we can progressively increase the fidelity of our models and tests. So engineering create is fundamentally about creating evidence. Each calculation, model, simulation, experiment, and prototype should reduce uncertainty and increase our confidence in the design. We have explored the technical solution and created engineering evidence. Now comes evaluate at the engineering level. Here, the question is no longer simply, does it work? The much more important question is, does it meet the specification? A washing machine may successfully wash clothes and still be a poor engineering design. Perhaps it uses too much water. Perhaps the motor overheats. Perhaps vibration exceeds the allowable limit. It may be too noisy, consume too much energy, fail the required lifetime, or violate a safety requirement. That is why engineering requirements must be measurable. We compare our calculations, simulations, experiments, and prototype measurements directly against those specifications. For example, if the drum requires 12 Newton meters of torque, it is not enough for the motor to turn the drum once. We must demonstrate that the required torque is available under the specified load and operating conditions, preferably with an appropriate design margin. The same principle applies to strength, temperature, vibration, accuracy, energy consumption, reliability, safety, and every other important requirement. If a requirement is not met, evaluation sends us back around the engineering loop. We investigate the cause, modify the design, create new evidence, and evaluate again. When the important requirements have been verified with sufficient margins and evidence, we gain something much more valuable than a working prototype. We gain performance confidence, and that confidence allows us to move toward manufacturing.
We now move into manufacturing, and once again, the meaning of explore changes. During thinking, we explored the problem and possible concepts. During engineering, we explored how the selected solution could technically work. Now we ask a different question. How can we make this product repeatedly, reliably, and economically? This requires us to explore the production process itself. For our washing machine, we investigate how parts will be formed, machined, molded, welded, coated, assembled, inspected, tested, and serviced. We examine materials, tolerances, tooling, fixtures, assembly sequence, suppliers, production equipment, automation, inspection methods, and cost. This introduces two important engineering disciplines: design for manufacturing, or DFM, and design for assembly, or DFA. DFM asks whether each part can be produced reliably using practical processes, materials, and tolerances. DFA asks whether the product can be assembled simply and consistently, perhaps with fewer parts, fewer fasteners,
easier access, and less opportunity for human error. A design that performs perfectly as a prototype may still be a poor product if it is difficult or expensive to manufacture. This is why manufacturing knowledge must influence the design before production begins. At the manufacturing explore level, we are therefore not simply asking, can we make it? We are asking, can we make it repeatedly, at the required quality, at the required rate, and at an acceptable total cost? That change in question is what turns engineering thinking into manufacturing thinking.
We have explored how the product should be manufactured. Now we move to create at the manufacturing level, and this introduces another important change in engineering thinking. We are no longer designing only the product. We are also designing the system that will repeatedly produce that product. This means creating detailed engineering drawings and tolerances, the bill of materials, process plans, tooling and fixtures, assembly procedures, work instructions, inspection plans, and production layouts. Consider a simple dimension on our washing machine. During engineering, we may determine what that dimension must be for the mechanism to function correctly. During manufacturing, we must go further. How will that dimension be produced? What tolerance is realistic? How will it be measured? What tooling is required? And how do we ensure that hundreds or thousands of parts remain within that tolerance? The same thinking applies to assembly. We define the sequence of operations, tools, tightening requirements, inspection points, safety procedures, and acceptance criteria. We may then create a pilot production plan so that the entire manufacturing system can be tested before full-scale production. This is a major transition. A successful engineering prototype demonstrates that we can build the product. A well-designed production system demonstrates that we can build the product repeatedly. So manufacturing create is not simply about making more units. It is about creating the processes, documentation, tooling, controls, and capability required to produce the right product at the right quality every time. We have designed the production system. Now we must evaluate whether that system is actually ready for production. This is very different from evaluating an engineering prototype. One successful prototype tells us that a product can be built. It does not tell us that hundreds or thousands of products can be built consistently. That is why we conduct pilot builds using the real processes, tooling, equipment, suppliers, operators, and inspection methods wherever possible. And now, variation becomes extremely important. We examine process capability, first pass yield, defects and scrap, cycle time, throughput, equipment effectiveness, supplier performance, cost, safety, and quality. For example, suppose a critical dimension is within tolerance on one washing machine. That is not enough. We need to know whether the manufacturing process can keep that dimension within tolerance repeatedly across many units, different operators, shifts, material batches, and production conditions. This is why manufacturing engineers use measures such as process capability, yield, variation, and statistical process data. If the pilot build reveals problems, we do not simply inspect the bad products and remove them. We investigate the causes and improve the production system itself. That is an important principle. Quality should be built into the process, not inspected into the product afterwards. When the process becomes stable, capable, repeatable, and economically viable, we gain production confidence. Only then are we truly ready to move from building prototypes to manufacturing products at scale. We can now bring the entire module together. Explore, create, and evaluate are the same three activities throughout the TEM Design Spiral. But what we explore, what we create, and what we evaluate changes as the product matures. During thinking, our main concern is whether we understand the right problem and have selected the right concept. We explore the problem space, create alternative concepts, and evaluate those concepts. The result is concept confidence. We now have evidence that our proposed concept is worth developing. During engineering, the question changes. Will this solution actually meet its performance, safety, reliability, and other technical requirements? We explore the technical solution space, create engineering evidence, and evaluate the design against specifications. The result is performance confidence. Then, during manufacturing, the question changes again. Can we make this product repeatably
at the required quality, cost, and production rate. We explore how to manufacture it, create the production system, and evaluate production readiness. The result is production confidence. Notice the progression. We are not simply adding more detail to the same design. At every level, we are asking different questions, using different tools, producing different outputs, and demanding stronger evidence. And each level reduces a different type of uncertainty before we invest further. That is the deeper meaning of the TEM design spiral. Explore to understand, create to learn, evaluate with evidence, then move forward when you have earned the confidence required for the next level.